is like this. Okay, so let's have a look at the first problem. What you have here is a picture of a square, and you also have the points on the sides of the square, which have been chosen. And these points are midpoints of the sides. In other words, midpoints is the middle point. And because all the sides of a square are all equal, you can put the same length in all the four sides. Okay, so these are the midpoints. And then these midpoints are joined, like this midpoint is joined to that, and so on. So quite a few of those lines are joined to create this picture here. And the question is, you are asked to find what fraction of the square is shaded. Okay, now whenever you have a question of what is the ratio of, or what is the fraction, you can always choose a number and say, let something be a number, maybe 100 or 10 or something, but just one choice you have. And then after that, you can do everything and you calculate it. You don't have to use a symbol. You can use a start off with a particular number and then develop the whole story behind that. Like in this example here, I don't know the side of the square, but they say what fraction of the square is shaded. So it turns out that it's useful to have 2 here, 2 and 2, all right? Because these are equal. So all these equal sides are all equal to 2. And now, using that, you must try to find out what is the area of the shaded region. Now, a little bit of thought will tell you the shaded region looks very, very nasty. You know, it's a very strange shape. But a little bit of thought will tell you that what's outside the shaded region, right, are these triangles, this triangle, this triangle. You'll see you've got 8 triangles. On each face, there are 2 triangles. So there are 8 triangles. And now, if you know the area, the total area of the white part, which is made up of 8 triangles, then you know the area of the square, because we've just said the side is 4. And all you have to do is to subtract the 16 minus the unshaded part, and you will get your shaded part. So I need to work out the area of these triangles. Now, again, if you look at these triangles, you can actually prove that they are congruent. Now, what's the reason for that? See, so let's give a name to this. Let's call this X here, and we'll call this Y. So you got the side 2. Now here you got side 2. Let's see. Are these 2 equal to X and Y? Right. So if you think about this, see, if you look at this triangle, which has got these vertices, right, that is a right angle triangle. One side is 2 and the other side is 4, right? Now you will see there are quite a few such triangles here, where you have to take 2 points on one side and take the vertex as a point on the other side. Like for instance, you can take these 2 and you take this vertex, and you will see that you've got 2, 4, and right angle. So again, those 2 triangles are congruent because the sides are equal and it's 2 sides and an included angle. So on every side you've got those 2 triangles. On that, so there are 8 such triangles. Okay, all of them are congruent. Okay, so in particular, if you take this triangle here, which I am indicating, right, and take this triangle here, those 2 triangles are congruent. The sides are 2, 4, and there's a right angle, which means that this angle here is equal to that corner angle. So this angle here is x. Right? Now, if you call this angle here y, okay, let's call this angle here y. Right? It means that, no, I can't call this angle y. I already named this angle here y. Uh, yeah. So this angle here is x. This is y. But you'll notice that, let's have a look at this angle here. This angle is also x. Because this triangle here, I'm sorry, this triangle is one of those triangles we were speaking about. Its sides are 2 and 2, 4 and right angle. So this angle must be x, will be the same as this angle here. Okay, but now you can see that x plus y is 90 degrees. See, because x plus y, there are two angles of this right angle triangle, 90 degrees. So this thing is also 90 degrees. See? So that's interesting that these lines here, they cross each other at 90 degrees, because I've shown that if you call this x and you call this y, then you've got a right angle triangle which has got those at the sides. Okay. All right. So in the same way, you can prove that you see, like if you compare this triangle, that one, and this one, those two triangles are also congruent. That right angle triangle and this right angle triangle. Okay. This is in this right angle triangle. And in this right angle triangle, you got this. So this angle is also x. See? And you'll have the same reasons will give you 90 degrees, and this will be y. So you'll see these triangles are congruent, right? Because you got a right angle and a side and two angles. Okay, so all these triangles are congruent. You can see here I've got an x here, and this will also be 90 degrees, and therefore this will be a y, and so on. So all these white triangles are congruent. Okay, so unshaded area. Now these are the right angle triangles. So it'll be eight times the area of the white triangles. All right, now I'm going to remove the x and the y because it's coming in the way. But now you must know that all those white triangles are all congruent. So I'm going to give a name to the sides now. Because I want to find the area of this triangle. So let's call this side here A and call that side there B. Okay. So the area of this triangle is a right angle triangle. One side is A, one side is B. So it's half AB. But all these triangles are congruent, these 8 triangles, right? So it's 8 of those triangles. So that's the unshaded area. It's 8 for AB. Okay, so therefore, the shaded area is the whole square, which is the area of a square is side squared, and the side is 4. So it's 4 squared minus the unshaded part. So, okay, so now we need to work out what is 8 times B? What is AB? Right? Now, so that's the shaded area. And the ratio, this is what fraction of the square is shaded. So you're looking at, the fraction is 16 minus 4ab over 16. Okay, the shaded area over the whole square. Okay, now we can actually calculate this A and B here. The reason being that you'll see that, see this triangle here, this angle, which we call X actually before. Right, now, hopefully we're going to use a little bit of trigonometry here, because the tan of that angle, tan of X, is A over B. Opposite over adjacent, tan of that angle, right? But if you look at the large triangle, this is also a right angle triangle here. And this angle here is an angle in the large triangle. And the tan of the X, you can see exactly what it is because it's equal to 2. The opposite in the large triangle, right, is 2. And the adjacent is 4. So you got that. This is 1 over 2. So from here you get that. If you cross multiply, you get B is equal to 2A. So B is equal to 2A. All right. So I can replace the B here by 2A. How did you get B equals 2A? Because we used trigonometry and we said the tan of the angle, we found it in 2 different ways. Okay. So in place of that B, I can put 2A. But now you have a right angle triangle, and that hypotenuse is 2. So if you use the Pythagoras on this, you have that A squared plus 4A squared is equal to 4. This squared plus that squared is square on the hypotenuse. So 5A squared is equal to 4. So therefore, A squared is 4 over 5. Okay. So this fraction that we're looking at is 16 minus, and we saw that B is 2A. B is 2A. There it is. So in place of B, I can put 2A. So I have minus 8A squared over 16. Because B is 2A, you see. And then we just got that A squared is equal to 4 over 5. Okay. So if you put A squared is 4 over 5, then you can get the answer to this problem. Now you can substitute. Then we can get our fraction is equal to 16 minus A squared is 4 over 5. So it's 32 over 5 over 16. And then if you simplify this, you'll get 3 over 5, which is the answer. Right. So it's quite a long-winded problem, but you have to notice that you concentrate your attention on this white square because there are 8 of them. And once you got that, then you solve the problem. So that is why I was focusing on this problem here to say if this is A and this is 2A, then there are lots of congruent triangles. So we use a lot of congruence with this as well. Okay, now I want to get on to the very last problem, last 2 problems, because those problems were easier. And I want to tackle those problems first before getting on to the next few ones. Because yeah, in this problem, you don't really have a construction. Okay, now this problem says find the volume of a cube. So you've got a cube, all the sides are equal in a cube. I might have mentioned that you call the other one a cuboid, but this is a cube, all the sides are equal, all the angles are 90 degrees. Whose diagonal, so the diagonal is drawn with this dotted line. Right. Now you're taking one corner of the box and you're joining it to the opposite corner. And that's the diagonal. So this line here is inside the box, right? It's not touching any surface. Okay, and you know that the length of the diagonal. That is all you got. And now the question is, find the volume of the cube. So that's interesting because there's only one information that is given. So how do you find the volume of the cube? All right. Now, obviously, you know, you have to give names to the sides because the volume of a cube is length times breadth times height. So all the sides are equal, and you can say, let the side be x. So the volume we're looking for is x cubed. So now how do you find x? Okay, so that's the challenge. How do you find x? Let's start on this bottom here. This bottom part is a square, right? And I can join those two opposite corners of that square. When I do that, you see, this line here is perpendicular to this line here. Let's call this R. This is a very important fact about what you call 3 dimensions. Like this is the floor now, where the cube is sitting on the floor, and you know very well that this edge here is perpendicular to the floor, right? If you put a box, you'll know that where the box turns, that line, that vertical line, is perpendicular to the floor. In particular, it's perpendicular to all the lines. So this angle here is perpendicular. See, when you got a floor space, and you line like this and it's perpendicular. All these angles are all 90 degrees because this line is perpendicular to every conceivable line on the floor which meets at this point. Okay, so then we can calculate QR squared. QR squared. Now remember, this is a cube here, so this triangle here on the floor is a right angle triangle, where the bottom part is a square. So QR squared is x squared plus x squared by Pythagoras. All right. So now, why did I need QR? Because you see, this triangle here, PRQ, is a right angle triangle. We just said that PR is perpendicular to this. So it's a right angle triangle. We know that this side is x, and we know the square of QR, which is fine because if I'm going to use Pythagoras, I will have the PQ squared, right? That's the one that we are given. PQ squared is equal to PR squared plus RQ squared. All right. And now PQ is this. It's cube root of 17 times square root of 3. Another nasty piece of work. And that's PQ. So if you square this, you're going to get PR squared. PR is x squared. And RQ, we just saw RQ or QR is 2x squared. So there it is. You got your equation in x, and we need to work out that one, right? Okay, let's see whether we can do this thing in a simpler way. You got 3x squared. I'm going to put this on the left-hand side. If you square this now this is 17 to the power of 1/3. And square root of 3 is 3 to the half. So when you square this, your rules of indices will tell you that this is 17, 1/3 times 2. Third law of indices. A to the power of B, all to the power of C, is A to the power of BC. So you got 2/3, and 3, square root of 3 squared is 3. Or otherwise, 3 to the half all squared is 3 to the 1. Right? Straight like that. So this is 3 here. This part here is 3. Those 3's cancel off. And you have that x squared. There's a 3 on the left-hand side. So you got x squared is simply 17 to the power of 2/3. That's x squared, right? And this one here is 3, and that cancels off with this 3. Okay, now you can get to x cubed straight away. Because it's from square, you can go to cube by simply raising it to the power of 3/2. So when you raise it to the power of 3/2, 2 times 3/2 is 3. Okay, so you can bring an x squared here. But we already know that x squared is 17 to the 2/3. And then you're going to raise that to the power of 3/2. And using indices, you've got a to the power of b, all raised to the power of c, is a to the power of bc. That's the third law of indices. So 2/3 times 3/2, they happily cancel. And you just have 1. So this is 17 to the power of 1. And that's the answer, because we needed to work out x cubed. So you have a very nice, happy answer to this problem, because although the number given is nasty, but in the end you get a good, nice answer. All right, so that is how you do it. Just to recap, what's important is that when you got 3 dimensions, what we call 3 dimensions, this is the vertical side of a box. It is perpendicular to every line which you draw on the floor of the box, right? Every line is perpendicular to it. That's an important fact, right? And then to solve this problem, you can't solve it all by itself. You have to join this part here to R to create a right angle triangle. And then you can calculate, you'll have your equations. Okay, so that takes care of that problem. And the next problem, as I promised you, is so in this problem here, you got lots of angles which are given. I've already shown what the angles are. So I don't have to read that question all over again. The information is given in the picture. Okay, so what do we have? We have this equals this. So you have an isosceles triangle, KAS. You also have that this whole angle is 75 degrees, KAS, angle KAS, angle KAS. So that is 75 degrees. And you're given that this angle here is 65 degrees, angle KTS. So the question is, what is angle ATS? What is the little angle? Okay, now this is very easy, because all you have to do is just know the facts about isosceles triangles. In an isosceles triangle, if 2 sides are equal, then the angles opposite the sides are also equal. And conversely, if 2 angles are equal, then the sides opposite equal angles are equal. So in this picture here, let's start here because those are the only two lines we have. We've got an isosceles triangle. So this angle here is 75. So therefore this angle here must be 75. Right? Because they are the so-called base angles. Although they're not base here anymore, they are standing up in the air. So we say the angle opposite the equal sides. This 75, opposite this is 75. So these two angles you can catch. But once you've got two angles, yeah, just have to chase. 75 plus 75 is 150. So therefore this is 30. This angle here, from here to here. Right. So if that is the case, then you got this whole angle here, must be 50. Because this entire angle is 80. Right? Now, if this angle here is 50, if you look at this triangle here, KST, you've got two angles in the triangle. This is 50, and it's given that this is 65. So you've got two angles of this triangle here, KST. So angle KST is 180 minus 50 plus 65. And so you add these two angles, subtract it from 180 to get this angle here. Now when you work this thing out, you get 65. So this angle here is 65 degrees. But now you got the two angles are equal, the base angles are equal, 65, 65. So therefore you can conclude that the sides opposite these angles are equal. So the side opposite 65 is one stroke. The side opposite this is also one stroke. So those two are equal because the base angles are equal. But the theorem by isosceles triangles, those are equal. Now you have a new isosceles triangle. See? Right. You got a new isosceles triangle, which is TKA. And you know this angle, this whole angle is 80. It was given. And so therefore these two angles, the base angles, they add up to 100 degrees. Because this is 80. And these are equal. So these two equal angles add up to 100 degrees. So each one of them must be 50. So we are at this stage here now. This is 50, and this is also 50 here. But now, if you know that this is 50 and the whole angle is 65, so this angle here is what you're looking for. It has to be 15 degrees because this entire, this was the problem. To find angle ATS, you have to subtract it from, subtract 50 from 65 because these two angles add up to 65. So this is a lot of angle chasing, what we call angle chasing. And also it's an application of the theorem of right angle triangles. Where lots of isosceles triangles. So we use the theorems on isosceles triangles to solve this problem. Okay. So those are the two problems that I was wanting to tackle before we go on to right. So this is problem number 2. Actually, it's problem number 4 because I've done 2 problems in addition to the first one. So we're now in problem number 4. So we're given a large circle and O is the center of this large circle. Calculate the area outside the smaller circle. Now, and maybe within the large circle. I would imagine that is the case. So you have to calculate that area. We don't know the radii. If I knew the radius of the small circle, and the radius of the large circle, then I can subtract these two areas, the small area, take it away from the large area, and you'll have exactly what I'm looking for. So the required area is equal to the area of the large, I'll put L, minus area of the small. Right. The area of the large is pi r squared. Both are circles. So we need to calculate this quantity, but we don't know either capital R, which is the radius of the large circle, R, respectively, small r, is the radius of the large circle, but you have to put respectively small circle. So we need to calculate these now. So that's the challenge. How do you calculate these? We've got a couple of pieces of information here about the circle. You've got two lengths. Are those lengths sufficient to calculate the big radius and the small radius? So let's investigate that. And to do that, you have to look for equations. Okay, we've given names to the large radius. And the radius of the small circle is there, but you can't see it too clearly. This is the center here. Okay, that is the radius of the small circle. And we need to calculate that radius. We need to calculate the larger radius. But now, if we call this small r, and this thing here, capital R, right. Now, can we write down some equations? I have to think very carefully here. You see, if you look at yeah, this is 18. What is 18 equal to? 18 is equal to the large diameter minus the small diameter. Right? If you take 18 and if you add it to the small diameter, you're going to get the large diameter. So 18 is actually equal to the diameter of the large circle is 2r. We said r is the radius. And the diameter of the small circle is 2 small r, as you can see. So there it is. You have an equation. So the equation is r minus capital R minus small r is 9. So that's the difference between these two areas. All right. Now, so that gives me an equation involving small r, capital R. If I got another equation, then I can solve, right? Then you'll have two equations and two unknowns. But you've got one equation here only in two unknowns. So where is the other equation? The other equation is really here, Pythagoras. But Pythagoras, right, you have that squared plus that squared is r squared. Okay, now what is this? Let's call this AB. Okay, so you have that what is AO? AO is actually equal to, yeah, there it is. It's from there to there. Sorry. The center of the large circle is O. Okay, so if you look at AO, it's equal to the full radius, the large radius, there's it here, minus the small radius. So it's the large radius, which is that, there's the center of the large square, and this is the center of the small square. So it's this minus this. And we have symbols for that. The large radius is capital R, the small radius is small r. Okay, so now we are set now to use the theorem of Pythagoras. It's r minus r. Sorry. But we already calculated r minus r, so that's 9. So that's very nice. Because we just calculated capital R minus small r, and we know from that now that capital R minus small r is that, and that's 9. Okay, so can we use Pythagoras? Well, you have that AO squared plus OB squared is equal to r squared. I'm going to put r squared on this side, right? So r squared is AO squared plus OB squared. Now AO squared is 81. So we just calculated AO. It's 9 squared if you like. And OB, what is OB? OB is the large radius minus 10. OB is the large radius minus 10. See how you brought in the 10 and the 9, and the 10 and the 18 into this argument. Okay, so you have small r squared is equal to 81 plus, now capital R, I need to get an equation involving only small r. I've got a capital R here, but capital R can be found because we said that this difference is 9. So capital R is actually equal to small r plus 9. So r minus 10, you can work it out as r minus 1. So here you've got r squared is equal to 81 plus r minus 1 squared. Because it's r minus 10. See, r minus 9 is small r. So r minus 10 is you have to take away one more. Okay, so you got an equation here. Right. It took a long while, but you got an equation. In fact, the r squared will cancel, and you will have that r is equal to 41. No, r not equal to 41. You got 2r minus, yeah, r is equal to 41. Okay, and then your capital R is small r plus 9. So that's 50. So you have your small r and you have a capital R, and therefore we can make all the other calculations. You see? So we said right in the beginning that the required area is pi r squared minus capital R squared minus small r squared. So if I take out all these things to create some space here, okay, so this required area is pi into r minus r into r plus r. I'm factorizing this because we already have that r minus r is 9, right? We use that earlier on. There it is here. And r plus r, we have these values. They are 50, 41 and 50. So this is 91. R plus R, we got these values. So it's 41 plus 50. Okay, so that is your required area. If you multiply this thing out, you get 890 pi. So here the problem was you had to perform a construction here. You have to join this to B, so you get the triangles which are for which the information is given. So you certainly need to draw this triangle. And while we're at it, we might as well assure. Sorry. Okay, so that's the answer to the problem. Okay. I'll get on to the next problem now. So here you have, looks like a very simple problem. The problem tells you that you've got an angle C is 90 degrees. This angle here, BDC, is 55 degrees. And there is at 125, this angle here is 125. This angle is 125. It's 55. That is 45. And you're asked to find the area of ABCD. Now that's quite a problem. Oh yes, it is also given that this is 20. Yeah, BC is 20, right? So I'm recording it on the picture. Only one number is given, and you're asked to calculate the area. Okay. Now this is a good problem to show you how you have to use logic and think and get to the get to the answer. Right? And you think, hey, 125 degrees, 55 degrees. You can't do anything with that. They are not like 30 degrees and 60 degrees and 90 degrees and 45 degrees. At least 45 is a decent angle. We know some things about that, but 125. But the one thing you can observe is that when you add these two, 125 and 55, you're going to get 180. Now that's a big plus, right? Which means that if I extend this line, this angle here is 125. Okay. All right. So then you say, well, wait a minute. You got 125, 125. And this side here is common. Why don't we try to create some two congruent triangles here? So I've extended this, but I haven't said how much I've extended it to. So why don't I extend it to the same length as AB? Why do I do that? Then I've got a common side. I've got this double stroke, and included angle is 125 degrees. So, and here I got double stroke, that included angle is 125 degrees. And from congruence, these two triangles must be congruent. Right? Which two triangles? The triangle ABD and so triangle ABD is congruent. So let's name these things nicely. AB is going through double stroke, so you must go through double stroke. But we should start with ED, sorry, triangle ED. D is at 125. It's the same as B, which is at 125. So you have EDB. These two triangles. You got a side, and the reason for congruency is two sides and included angle. So there we use the fact that this is 125, you see. So this is a very powerful thing. Now these two triangles are congruent. And this angle here is given to be 45 degrees. So therefore, this angle here will be 45. Why? Because of congruency. Therefore, we can say angle E is 45 degrees. You see, angle E is opposite BD, and the angle opposite BD in the other triangle is 45 degrees. So they both correspond to the same side. But wait a minute, you got a right angle triangle here. And this angle is 45. So what does that mean? It means that this angle here is also 45. And the remaining angle of this right angle triangle. This angle 45 is an angle in a right angle triangle. So, but now you've got a triangle with two sides of 40, with two angles of 45. It's a right angle triangle. So it must be an isosceles right angle. So this part here must be equal to 20. And lo and behold, we got an isosceles triangle here. Because this is BC is 20. Well, we already had this isosceles. So now, what is the question? The question is to find the area of triangle ABCD, of quadrilateral ABCD. What is it? ABCD. Now, let's analyze this area here. ABCD. Now, it's made up of two areas. One area is the area of that, and the other area is made of this rather sharp-looking piece, which I'm going to paint green. So area ABCD is equal to red plus green. No, I'm sorry, blue plus green. Okay, I'm using very loose language here. But the green triangle, we've just investigated that triangle. It's congruent to BDE, right? So this triangle ABD, that's your green triangle, is congruent to BDE. So they must have the same area. See? So this area here we're talking about. Right. That triangle is congruent to the green triangle. Okay. So therefore it must have the same area as green triangle. So now you got the blue triangle plus the red triangle. The blue triangle and plus the red triangle is just the area of triangle BCE. And the blue triangle plus the red triangle is a lovely area. It's an area of a triangle BCE. And we just found that this is a right angle triangle. So if you work out base, half base, which is 20 times the height, because now we know the sides of this, and so that's the area. 200 square units. If the units are not given, you must say, whenever you talk about area, you must put out the final answer will be square something. And in a cube, the volume, you'll say it's so many cubes. Okay, so this is a nice problem where you exploit the fact that 125 plus 55 is 180. So that allows you to extend this thing and say that this exterior angle will be 125. And then you notice that there are two triangles which are congruent here. But there's a very important construction. And that must be outlined right in the beginning, even before you start. Right? The construction. Although it comes up later when you work out the solution. The construction is extend CD to E. You see, you must be very clear there. You can extend it to CD to E, but you can't stop there. Because how far must you go in your extension? So you say so that DE, right, is equal to, we said that is equal to BA. So that's the construction. And you use the construction to solve this problem. Okay. So although this problem looks quite harmless, but to find the area, quadrilateral, when you try to use you might be able to use a calculator to get the answer, but you're not allowed to use a calculator. That's a problem. Okay, so let's get on to the next problem without much further ado. Now this one was quite a challenging problem. If I remember correctly, it occurred as the very last problem in the second round, Senior second one. In some year. Okay, what is it? It's given that you got a square. You got a square. In fact, two squares are identical, and you got this little square drawn inside it. In one case, you produce these lines, you get a new square and you call it S. And here, what you do is you draw a square whose diagonals, they say the diagonals of square T are parallel to the sides of the other two squares. So this diagonal here is parallel to that one. And this other diagonal is horizontal. So it's parallel to that side. Okay, so now you are given also the side length of square S is 27. So that allows you to calculate the area of S. It will be 729. 27 times 27. You don't have to work on 729. You can do everything just by canceling fractions. Right? And the question is, what is the area of square T? What is this area? Now, I tried out various methods, try to analyze the geometry of this, and it's quite complex. But ultimately, I came to this, which helped a great deal. What I did was, I sort of completed the square here, like this. So put this square here into an horizontal square. Okay? I didn't mark the thing too accurately. Let me. So that is what you do. So now you got this square here. Now let's analyze that. Then what I do is divide that square up into 16 smaller units. And I've got the diagram here. So I'm looking at this small diagram here. I've now expanded it to get to this thing here. Right? This is what we had originally. Can you see? There's your T. So this T now is this blue square. So we need to calculate the area of the blue square. So how do you find that? So in the same diagram, I've drawn the S also. There's S here. You see this vertex for S, there it is. It is sitting on the side of this other square. See? So that's why I got this red point here. Right? It's the same as this point here. Okay. And this top point is the same as that. Okay. So I want to calculate the area of the blue square. We know that the length of the red square, this one here is 27. Square S, yeah, square S is not the tilted square. Okay, so in other words, you know the area of what I'm going to call this the red square. Okay. So we know the area of the red square. is equal to 27 times 27. If you don't know it, it doesn't matter because we probably will need to. It'll cancel out with the fractions. Okay, so bearing that in mind, what is now? I'm going to call this side here A, right? The side of this red square. Okay, area of red square is that. Let me see what it is. It's actually equal to A squared. Right? Now, one of the things that these two squares share is, you see this diagonal of the small square. It's part of the diagonal of the large square. All right. So I'm going to explain that. Why is it part of that? If I extend this line here, it's going to go through H. The reason for that is the if you join H and A, you're going to get the diagonal of the large square, right? And so this angle here is 45 degrees. See, so so when you extend this thing here, this angle is also 45 degrees, right? Because this is the diagonal of the small square. So when you extend this thing, it's going to go up there because these lines are parallel, you see. So it'll go up to that point. Okay, now the area of the red square is A squared. Okay. Now let's call this other thing. Oh, okay. Now this A squared is actually, if you look at the diagonal of the AB squared, AB squared is A squared plus A squared. You see, I've got, it's a diagonal of the red square. So it is the square of the diagonal. So the AB squared is 2A squared. Right? Now that tells me that the red square area, right, is 2A squared. And that is equal to 27 times 27. Okay, so now you can actually calculate A squared. A, remember, is the side of the small square. So we got the area of this is, so we know what A is. Now, if you look at this thing here, you see, these, you got a small square here, E, F, G, H. It's a square. I've divided it up to all four equal parts here. And you'll notice that B is where these two diagonals intersect. Right? The diagonals of two squares, of the two diagonals of the square here, E, F, G, H, this is intersect. And you know that they will bisect each other. So what does that mean? It means that this length here is equal to that length. And these are equal like this because, again, for the same reason, a diagonal of a square, two diagonals intersect, they bisect each other. So you'll have, this is the diagonal of the small square here, and this is the diagonal of the square. So you see all of them are equal. So AB is actually equal to 3/4 of AH. because from what I've just said now, there are 4 pieces here, and AB is 3 pieces. So 3/4 of AH. And we need to calculate the area of T. So the area of T, we can say, is B squared. If you call this B here. But this is also B, because you're working in a square. So once again, you have an equation with the diagonals here. Now you've got B squared plus B squared, AH squared. That's your diagonal of the large square. It's equal to B squared plus B squared. That squared plus that squared is 2B squared. All right? We're just using Pythagoras. But now we have, we've got everything now, because we know that 2A squared, we know what that is. And we also have AH squared. So you have AB squared is 9/16, squaring it, times AH squared, and AH squared is 2B squared. Okay? But AB squared is this. We just saw it's equal to 27. Well, AB squared is already, no, that's 27 squared. Oh, it's 2 times 27 squared. All right? 2A squared. AB squared is 2A squared. So A is given to be 27. Which area was 27? The side length of square S. Oh, I see. This is 27. So this part here is 27. Okay, so A is equal to 27. Yeah, that's right. So now you've got your B squared, because you're trying to calculate the area you're looking for. So B squared is equal to 2 times 27 times 27. Right? And then 2 goes into this 8 times. So you multiply this by 8 and divide by 9. B squared. 2 goes into this. So to make B squared the subject, you multiply on both sides by 8, divide by 9. And what do you have? 3. And when you work this out, you get 648. Actually, you have B squared is A squared over 2. Yeah, so you have to, sorry, there's another 2 here. Okay. Yeah, because B squared is AH squared over 2. All right. Anyway, you can fill in the details here. It's rather complicated. There are other ways of solving this problem which are even more complex. But I found that the key thing here in this is that, let me just take this thing out, because I've been floundering around, but the basic fact here is to find the area of a square. Right, which is not used very often. Area of a square We know it's a side squared. Right? But the side squared is 2 sides squared is equal to d squared. So this is half d squared. So the area of a square is half the square of the diagonal. So that's actually what we are doing. So this red area is half the square of the diagonal. So AB squared. Right? And we know the red area is 729. It's given. And then the area we're looking for, area of T, is the blue area. Right? And we saw that uh, this is the blue area is okay. The area of the large square is half that diagonal square, right? And that's how you eventually get to this. It's a little tricky. You have to sort of manipulate these things. Okay, well, that was the very last problem in round 2 in that year, so you can expect it to be a little bit difficult. Let's get on to the next problem. The next problem is this one here. It's the last problem we're going to do. And you got a stop sign. This thing here is a stop sign. You see these stop signs on the roads. A stop sign is actually a regular octagon. In other words, it's got 8 sides, 3, 4, 5, 6, 7, 8. Right? The opposite sides are parallel, you can see, like that. And you've got 8 angles, and all those angles are equal. Right? And what is the internal angle of an octagon? Internal well, the external angles, if you want, you can use that formula, but 2n minus 4 right angles. So it's actually, there are, you have to divide each internal angle. All the internal angles are equal. So each internal angle is 1/8 of the sum of all the angles. And the sum of all the angles is 2n minus 4 straight angles. Times 180. See, if there's a formula for an internal angle of any polygon, it's 2n minus 4 um, straight angles. Or is it 2n minus 4 right angles? I think it's 2n minus 4 right angles. Yeah. Okay, so you get 16 minus 4 is 12, 3/2. So you get 135 degrees. Okay, so all the angles of a regular octagon is 135 degrees. See? Now, actually, what has happened here is that if you extend this thing, you'll see the octagon is actually obtained by cutting off the corners of some square. See? And in the square, the diagonal of a square is bisects the opposite angle. So this angle here is 45 degrees. Now, what I've done here is that I've drawn this line. This is your height. The question was to find the height of the stop sign. The height, you will say, is really from here to here. But that's exactly the same as this. This is tilted, right? And the height is from one parallel line to the distance between these two parallel lines. The distance between these two parallel lines, obviously, the same as the distance between two. So the height of this is this entire red line, right? The full red line. So that is what we have to calculate. Now, to make that a little bit easier, what I did was I drew the red line, but I drew a perpendiculars like this, right? And then I tried to analyze this one. Then I saw that this angle here is 45. This angle had to be 90. This 45 because it's half a square has got its okay, maybe that's not the right way to argue it, but okay, but you can take it as read that this angle, when I'm dropping a perpendicular here, these lines are parallel. So you got a rectangle. This is equal to this because this is 90 and this whole thing is 135. We saw that. So therefore, that must be 45, each one of them. You've got a right angle triangle with one of the angles 45. So it must be an isosceles triangle. And that is why we can put x's here. We can put this equals that. So these x's are very important because your height that you're looking for is 50 plus 2x. It's this entire thing. So the question is, what is x? Right? And now x is easy because this is a right angle triangle. So these are two sides of a right angle triangle. So you got x squared plus x squared is equal to the side squared, which is 50 squared. Right? X squared plus x squared is the hypotenuse squared, but the hypotenuse in this picture here is just the side of this. All the sides are equal. They're all equal to 50 centimeters. It was given. So you have 2x squared is equal to 50 squared. So we need to calculate 2x. Now, a nice easy way of calculating 2x is, you know that when you square that one, 2x, you'll get 4x squared. So why don't we multiply both these by 2? Well, this is 50 squared. And then you'll get 2 times 50 squared. Now, this is 2x all squared. So 2x is equal to the square root of this. See, 50, the square root of 50 is 50, and the square root of 2 is square root 2. You can't do anything with that. So it's a nice trick. If you're looking for 2x and you got x squared, so you know that if you square that, you're going to get 4x squared. I got 2x squared here, so double it, and then you can come back to your 2x quickly. So this gives you 50 plus 50 root 2. So that's the height of this regular octagon. Okay, so that brings me to the end of this session 6. And the next question was really the assignment question. And the assignment's question is very similar to what we have done here. See, from a square with side lengths 5, triangular pieces are removed from the four corners, form a regular octagon. So if you look at what I've done here with the regular octagon, you'll be able to uh, get quickly to this solution to this problem. So you need to find the area which is removed, right? So I'll leave this to you, and your coordinator will come back to you with this problem, and that's the assignment problem for this week. Okay, today for once I finished exactly on time, 6:30, and I thank you all for attending. What's happening here now? Oh, let me stop share. That was a problem. Okay, so there we are. I want to thank Hansa. I think Hansa was one of the first ones to come in, or was it Hannah? Hannah, Ezra, and Derek, and Mr. Mutala. So